This session, we're going to cover an introduction to TCP selective acknowledgement. My name is John Pittle, and I'm Services CTO at Riverbed. And I'm really excited that you joined this session today. We're going to focus on really digging into this field because correctly interpreting this field can really help you be a better performance troubleshooter. And that's one of the things SharkFest is all about. In terms of the agenda for today, we're going to move through a few things pretty quickly and then really spend quite a bit more time on some of the details. I'll call out some of the relevant RFCs, and then we're going to make sure that we all have a solid, comfortable understanding of the basics around TCP acknowledgement. Then I'll get into the introduction of selective acknowledgement. We'll look at some decode details and examples. We're going to focus on creating Wireshark columns and filters and using colorization around SACK, which is extremely helpful features of Wireshark. And then I have what I hope to be a treat for you, some adventures from real life troubleshooting I did with a customer a few years back that really helps to illustrate not only selective acknowledgement in the decodes, but how it affects performance. So who's John? I've been practicing performance engineering since the early 80s, protocol analysis since 91, doing performance consulting since 2005. And I really enjoy the mystery of a complicated performance issue. So I am fortunate in that I get called into some of the more gnarly problems that we're trying to solve for our customers when they're having application or network performance issues, which is a real joy. And then last thing about me is I shaved off my beard in 2003, but that's the beard that I used to have. So let's go straight into the session. I guess I should mention Chris is moderating. Thank you again, Chris, for doing that. If there's questions during the session, please feel free to put them in the Q&A box. And then there will be a couple of placeholders where we'll have some time for questions and discussion, but definitely feel free to put those in during the session.
Cool, will do. Thanks, John.
Chris, thank you. So I'm hoping that everybody has heard of RFC 793. It's the original TCP RFC, and all enhancements to TCP all emanate from that as the original spec. Selective acknowledgement came along. I can't believe it. It's like more than 15 years ago in RFC 2018. It's a good read. It's important to know the RFC is there. You may have to refer to it from time to time just to make sure you're correct, feeling comfortable that you're correctly interpreting something. Hopefully this session will help you with that as well. And then there was an extension to selective acknowledgement in RFC 2883 that introduced something called duplicate SACK. And I'll talk about that for a few minutes in this session today as well. So let's start with a review of expected/normal TCP ACK behavior. And hopefully all of this will be like, oh yeah, we've heard this before. We're very comfortable with this, but I want to make sure we have this as a baseline, as a foundation. So as long as packets arrive in the expected order, the receiver will ACK every other packet. That's the default behavior. Sysadmins can change that behavior, but generally speaking, in most TCP stacks, that is the behavior you could expect to see. You might see some stacks that wait till there's a push and maybe something else that triggers it, but generally it's going to be at least every other packet. If a packet arrives out of order, or a segment in a packet arrives out of order, the receiver will immediately issue an ACK with a value equal to the sequence number that was expected. So let's say I'm expecting sequence number 10 in the stream, and I get sequence number 20. As the receiver, I will immediately ACK the packet that I received, and I'll say, hey, I just received something, but I was wanting 10 if I was expecting sequence number 10 in the stream. So normally every other packet, but if something's out of order, immediately ACK with a value of what we were expecting to get. And we will, as the receiver, will continue to ACK every packet that I receive until the expected packet is received. We'll ACK that, and then we'll go back to the normal behavior of default normal behavior, which is typically every other packet. And if TCP fast retransmit and recovery is turned on, after a sender receives 4 ACKs, the original plus 3 more, when the sender receives those, then the sender says, aha, there's something missing. I'm going to do a fast retransmit and retransmit the missing segment. So that's the normal expected TCP ACK behavior without SACK enabled. So let's look at an important term on the next slide. I want to make sure everybody keeps this term in mind as we go through the presentation and as you're working with Wireshark. And that term is cumulative ACK. Cumulative ACK. And it's important. We don't normally use the word cumulative ACK. We usually just say the ACK in the header. But the RFC calls it out as cumulative. And what it means technically, explicitly, literally, is the receiver says, hey, I've received everything in order up to the point when I'm sending you this ACK. And basically the receiver's declaring, hey, I have everything in order up to this point and up to basically ACK -1 in the stream. And I'm now ready for the value that I put in the ACK field. So I'm ready now for, in this case, I'm pointing to relative sequence number 40. I'm ready to, I'm ACKing everything up to 39, and I'm now ready for you. I'm ready to receive, and hopefully it's coming next, is stream at byte 40. So cumulative ACK, we're going to distinguish that today between selective ACK and cumulative ACK. So I want to make sure we get this term, everybody's comfortable with this term. So that's review of the basics. And now let's introduce selective acknowledgement. So RFC 2018 proposed an enhancement. And selective acknowledgement is super interesting because it allows the receiver to acknowledge segments that have arrived even if they're out of order. And in theory, the sender won't have to retransmit those segments if he knows that they've been received. At the very end, we'll see there's something called reneging that could potentially happen. But ultimately, the receiver is letting the sender know, hey, I've received these things. They're not in order, but I do have them. So you don't necessarily have to retransmit them. I just want to know, I want to let you know that I have them. But we can't communicate that kind of control level detail to the sender without a new field. So we now have a new field is needed in our header. And what you'll see is, in addition to all of the TCP options that were available prior to this RFC, we're going to add a new TCP option into the TCP header field that would allow us to declare up to 4 different contiguous out of order segments or segment ranges that we could declare from the receiver to the sender, that we could declare in the TCP options field. And you know, the TCP options field is a fixed size. You can't, I mean, it's variable up to a point, but it can't grow beyond a certain point. And if you have the option for TCP timestamps turned on and you have SACK turned on, then you'll only have enough room to put in 3 SACK segments. And we'll see some examples of that in the decodes. So how do you turn on selective acknowledgement? So it's pretty much on by default in most modern stacks. It is declared at connection startup time. So when you take a look at the SYN and SYN-ACK handshake, you'll see a flag that says SACK permitted, which means whoever is sending that flag, whether it's the client in the SYN packet or the server in the SYN-ACK packet, it's saying, hey, I'll process the SACK field if you send it to me. I support it. I know how to interpret it. I'm good to go. Interestingly, each side could independently choose. Typically, you're going to see it's on for both sides, but you might come across a rare case where you see it on one side, but not on the other. So the intended benefits of SACK is to inform the sender with better intelligence about the success of segment delivery. We definitely want to minimize the amount of unnecessary retransmissions. Hey, if the sender already received something, maybe it got out of order, but I know the receiver has already received a segment. Maybe it arrived out of order. If I'm lucky, I won't have to resend it. One of the interesting points, and I put a little key next to this, is that the use of SACK is not going to necessarily change the way congestion control works. In fact, I don't think I've seen an example where it defeats or modifies the behavior of what you would call typical congestion control, depending on which congestion control features are configured and negotiated. Any retransmission that you have may still have a negative effect on the congestion window and all of the related timers that are associated with retransmitting and influencing the congestion window size. And we're going to definitely see some examples of that as we drill into our field exercise. So you definitely want to be aware of this field. You want to be using it during your packet analysis. It does tell you important information. So interrogating the SACK fields is going to help you quantify the extent of out-of-sequence packets. Like 1 or 2 out-of-sequence packets, no big deal. But if there's a consistent and persistent out-of-sequence behavior, that could turn into some problems for you in terms of congestion control for the sender. So you want to know that it's there. You want to focus on the bytes in flight as a guiding metric, and we'll be looking at that in our example. If in-flight data bytes stay high, then you know you're not really having a congestion window problem. Maybe it could be even higher if you could arrange for some additional receive window. But as long as in-flight stays high, you're probably going to be in good shape. But if it constantly dips down and hits 0, or you frequently see TCP slow start, you may find that the root cause is really a severe out-of-sequence packet condition. It might not even be packet loss. It's just packets arriving significantly out of order. So it's important for you to be aware of these as you're doing troubleshooting and looking for the evidence of, why is performance so bad. So I've got 3 new terms for you on the next slide. And I like to kind of just give you a heads up. Hey, these next terms are important to the rest of the presentation and to your understanding of SACK. So Wireshark is definitely SACK aware. There's decodes for SACK in wonderful ways. So we can decode the SACK fields. We can explicitly filter on the SACK fields, color on the SACK fields. So here's the 3 terms that are important: SACK count, left edge, and right edge. So SACK count, left edge, right edge values can be, and you're going to see this in a minute, displayed as columns in the decode summary section. And you can also filter, particularly on the SACK count. Filtering on the SACK count is pretty interesting. All right, so let's look at an illustration of these concepts: SACK count, out of sequence packets, left edge, right edge. So we're going to start with a very basic, very simple illustration. We've got 5 packets. Each of them is 10 bytes in length. First one, packet 1, starts at sequence 11. Packet 2 is 21, 31, 41, 51, etc. And we're going to look at what happens using just some hand drawings of when things arrive out of order. In this case, in our illustration, packet number 4 shows up in at the receiver after packet 2, and then followed by packet 5, and then packet 3 finally shows up. So packet 3 arrives late. So packet 4 is going to be out of order, packet 5 is going to be out of order, and packet 3 is going to be the happy packet. So kind of just what might this look like if you were to diagram it out? The first 2 packets arrive with stream bytes 11 through 30. We're ready for 31. But instead of getting sequence, the stream bytes starting at sequence 31, we get stream bytes starting at sequence 41. So now we've got an out of sequence condition. So if you notice, the left edge equals 41, right edge 51, these are pointing conceptually to help you visualize where's the left edge, where's the right edge in this discussion. When packet 5 arrives, notice that it fits nicely right next to packet 4. And notice that the right edge now has moved out to 61, saying, hey, I'm ready for 61. But the left edge stays the same because that did not, we haven't received anything yet that would influence the left edge of this stream. And then finally, packet 3 arrives, it fills in that missing gap. And now all data is received up through and including byte 60. And the receiver is ready for stream starting at byte 61. So again, very simple illustration. We're going to build on this. It's going to get more complicated here in a moment. So let's take a look at some decodes around this left edge, right edge, and count field. So in looking at, we'll start with this selective acknowledgement. I'm going to try my Zoom pointer. Yeah, we're going to start here. So we've got at packet 38 here, we've got an ACK that says, hey, I've got a SACK count of 1. So TCP SACK count of 1. I've got a left edge of 17,619, a right edge of 19,043. We've got a cumulative ACK that says, hey, I just received something and I was really hoping to get the stream bytes starting at 14,771, but I didn't. I did get something. And what I got was starting from the left edge here to the right edge here. And if we look down at the decode level, you can see what the SACK block looks like. It's a little block that says, hey, there's a SACK block. There's a TCP option kind field, it's 10 bytes, and you can see left edge, right edge, and then the SACK is a Wireshark derived field. That field is not part of the TCP header. That's something that Wireshark puts on there for our benefit, makes it easy. So we've got our cumulative ACK up here that says, hey, I've received all of these bytes. I'm ready for 1477, but there's more information, and that's where the SACK field comes in to inform the sender of what actually did get received. So I've received this segment out of order. And how can I tell what's missing? If you subtract how would I say this? If you subtract the left edge from the, I don't think I did this. I don't, this is what's missing, but if you wanted to know like the byte count, you would subtract the bigger number from the smaller number to get the difference. So you'd subtract the cumulative ACK from the left edge. But these are the bytes that are missing from what I was expecting all the way up to left edge minus 1. So we're going to continue looking at examples like this. The other thing I want you to notice, and this is another kind of visual clue, let's say you didn't have these columns present. Well, one of the visual clues is the packet length. So when your TCP options field is bigger, you know, the packet length is going to be higher. So a length in this case of 71 is sort of a visual clue that, hey, there's something in that TCP header. And oh, by the way, this packet down here, this is actually even bigger. So there must be more stuff jammed in there. And you can see that in this case, there's a SACK count of 2 and 2 different segments that are being declared. So another heads up, doing several heads up in this presentation, prepare to observe some very awesome Wireshark features. So I don't know how much everyone is using apply as column, but it's like one of the most awesome things about Wireshark is being able to customize the decode columns the way that you want them. And in this case, for SACK, it's super simple. You just highlight the field that you want, you right mouse click on it, you then say apply as a column, and then before you know it, in fact, before you get your finger off the mouse button, it's already up there as a column. And then you can add the next one. And then of course, for the folks that have been through some of the basics training in Wireshark, you know, you can then save that layout as a part of a specific profile, which is very handy. Okay, so we were kind of looking at this visual of stream bytes moving back and forth and arriving out of order. Let's take a little bit closer look at the receiver side, TCP mechanics. So let's say up here we've got packet 1 arriving up here in the top right-hand corner of the slide, 11 bytes, length equals 10. First packet arrives in this stream, the receiver starts his delayed ACK timer and is now waiting for a second packet. And as you may know from delayed ACK timer knowledge, if there is no second packet, then as soon as that delayed ACK timer expires, we're going to send an ACK straight away to let the sender know that we did receive a packet. But at this point, well, we're now waiting for a second packet. So now packet 2 arrives, sequence 21, length 10. We cancel our delayed ACK timer and we send the ACK with a value of 31 that says cumulative ACK of 31, which says, hey, I've received all the way up to byte 30 and I am ready now and willing and able to receive stream byte at 31. So here comes packet 4 from our example. Wait a minute, it's out of order. We immediately issue the ACK because, why? And we already kind of talked to this a little bit, because what we just received is out of order. So now we send the ACK of 30, cumulative ACK of 31 saying, hey, I did get something. I was really looking for 31, but oh, by the way, just so you know, I did receive a segment starting at 41 through 50, and the next byte after that would be 51. So packet 5 arrives, but it's also out of order. So we immediately send yet another ACK because it's not the expected segment. And now you can see the SACK field expands. This matches our example a moment ago. Cumulative ACK 31, SACK 41 through 61. And at this point, the receiver TCP stack is holding some packets that it cannot hand off to the app. And I can't hand them off to the app because I have to deliver them in order. So the receiver's TCP stack that buffer space, I can't free it up. It's going to hold on to those 2 packets or more until I get the missing, the segment that I'm missing. So here comes packet 3. Now we can say ACK of 61. And there's no need for SACK at all at this point, because everything has been received in order up to stream byte 60. And I'm now ready to receive stream bytes starting at 61. Quick side comment. So I'm not sure. I think it's Discord that's chirping at me. I just want to make sure, Chris, that's not you trying to get a hold of me.
Nope, that's not me.
Okay, very good. Thank you, Chris. All right. So packet 3 arrives. Order is restored to the force. Everybody's happy. We're all good to go. And if you have not seen the Lego Star Wars, this is not a plug for Legos or Star Wars, but it's really funny. If you've never seen it, it's hilarious. Okay. Now we're going to look at a more complicated scenario before we get into some more before we get into our field study. So now we're going to look at 6 packets, 10 bytes each, 1 through 6, but there's going to be quite a bit of out of order nonsense. Can't tell you what happened in this theoretical non-existent network, but it's definitely misbehaving, and you can see there's absolutely nothing in order. 1, 3, 6, 4, 5, 2. Nothing is in order in this stream, in this burst of 6 packets. So let's load ourselves into the fun machine and see if we can feel good and confident about what this means to a receiver and how it's going to respond back with the left edge, right edge details to the sender. All right, so our first packet arrives, bytes 11 through 20, all is good. We start our delayed ACK timer, but all of a sudden packet 3 arrives. Well, wait a minute, I'm waiting for stream byte starting at 21. I'd really like to have that, please. I got something different than what I was expecting. So I immediately ACK with 21 saying, hey, that's what I need. But by the way, just so you know, I received 31 through 40 as in my receive buffer. So then packet 6 arrives because things are really, really out of order. And now notice I've got 2 different blocks that have been received out of order. So I send an ACK 21 and then a SACK with 2 SACK blocks, informing the sender that, hey, I'm still waiting for stream byte at 21, but oh, by the way, I have some stream bytes in one block at 31 to 41 and stream bytes at a second block of 61 through 71. Just want you to know I have them, but please send me 21. Now packet 4 arrives. And notice that one of our SACK blocks changes the right edge. Notice how the right edge of the first block changes from 41 to 51. So this block is still one contiguous block. It came from 2 different packets, but it's one continuous block of stream bytes. And oh, by the way, I did receive 61 through 70 as well. Packet 5 arrives, and now I've got, I still need the stream byte starting at 21. There's still a gap, but there's only one block of selective acknowledgement bytes being declared, which is starting at 31 through 70, and the next byte would be 71. So I'm still out of order, and then I wanted to, I don't think I can do this on the Zoom webinar. I want you to just think about for a minute, how many packets are in the sender's retransmit queue? And then I want you to think about how many packets are in the receiver's receive queue. So what's in the sender's queue, if you think about the whole retransmit mechanism, are things that I'm waiting for acknowledgement to occur, but there's a key point. Acknowledgement in order. So the cumulative ACK would, I believe, drive what the sender maintains in his send buffer. So even though we're selectively acknowledging certain stream bytes, the sender can't get rid of those until they're actually arrived in order. So they have to stay in the retransmit queue until we get confirmation that they've been fully received. And then on the receiver side, I can't hand off packets to the application layer because they're not in order, and they have to be in order. That's one of the promises of TCP. So there should be, in this, I wrote packets, but it's really segments that you should be thinking about. So there's four segments that are in the receiver's queue ready to be shipped off as soon as the missing piece arrives. And here comes the missing piece. Everything arrives. We can hand off to the application layer now. When the sender receives this ACK equals 71, he can flush his retransmit queue. He no longer has to hold on to those packets because sender has declared, hey, I've received those. I've received everything in order. So it's a wonderful thing. So we made it.
Hey, John, you do have one question. Just
Yes.
wanted to point that out while you're here.
Yep.
Can you see the Q&A window, or did you want me to read it for you?
Oh, here we go. No, thank you.
You bet.
Okay, Carl. Hi, Carl. In the example, the right edge in a SACK option is increased when the right edge bytes arrive. Is it valid to decrement the left edge if that is how the bytes arrive? Yes, it is actually, and I think we're going to see an example of that in my field case study. But yes, it could absolutely do that. Thanks for that question. Okay, so we made it through our example, and we're going to take a look at a few more decodes. So we're now going to take a look at what shows up in Wireshark when there's two SACK blocks and some really interesting ways you can manipulate the columns. So we'll drill in, we'll zoom into this box a little bit. So here in our TCP options, notice that we've got two different blocks. SACK count as 2. Also notice that the higher number sequences are showing up quote unquote first. There's not necessarily a specific order to be maintained or how the receiver reports back to the sender. These can change, and you'll see an example of that in the upcoming example. But what I want to do is I'm going back 2 slides because I wanted to just say, well, this is kind of ugly to look at, right? This is the left edge, and there's 2 blocks. So this is the left edge for one of the blocks. This is the left edge for another block. It's kind of ugly to look at. So in one of the SharkFests, I grabbed SACK and I said, dude, there has to be a way to split these up. This is just too hard to look at. It's hurting my brain. And I'm so glad I did, because number one, I learned something every time I talked to SACK, and he said, oh yeah, you can easily split them up into different occurrences. And then he showed me how, and I'm going to show you what he showed me. So with this profile of columns and column layout, notice we've got the SACK for left edge 1, SACK block, left edge 1, SACK block, right edge 1. So this is occurrence 1 in TCP options. And this is SACK left edge 2, right edge 2. This is occurrence 2 in the TCP options. And how do we do that? Well, first off, let's take a look at another cool Wireshark feature, which is when you edit a column, depending on the nature of that column and the context of that column, you may see this occur. Well, I think you'll always see occurrence, and it may always be 0. But if you're looking at a field that has multiple occurrences, you can pick and choose the one that you want to display. So in this case, we're looking at SACK left, what I titled SACK left edge 2. It's this field, TCP option SACK left edge, and it's occurrence number 2. So once you get used to dealing with occurrences, it's like, oh my God, this is great. I want to use this feature. I want to use it like all the time. So that's how we break out the blocks into the occurrences, each block into separate columns using the edit occurrence number operation. So you right mouse click on the column header, select edit column, and then you do your work here. You can also use coloring and filtering to change the color of the row, the packet row, based on the SACK count. So you can see in this example, there's a filter that says, hey, if SACK count is equal to 1, make it yellow. If SACK count is equal to 2, make it orange. And if SACK count is equal to 3, make it red. And I tell you, I mean, I'm a visual person anyway, so anytime I can use color to help guide my eyes to what's important to look at, it's always useful. So here's a view of what the colorization looks like. And there's also a filter here that says, hey, if you have a SACK field, let me just filter the display to only those packets that have a SACK field. And then you can see the coloring that was applied based on those colorization rules. So you can filter and you can color rows based on the SACK field. You could probably do it based on the bytes, but I'm not sure that would be useful at all. The count, using it for the count field is super useful. So a quick side note about RFC 2883. I forgot what year it came out. I had it in an earlier slide, but it introduced something called duplicate SACK. And one point to drive home, duplicate ACK has nothing to do with duplicate SACK. They're completely different mechanisms. They sound a lot alike, but they mean different things. The sender behaves in different ways. So the first thing to declare and take away from this slide is DUPACK is not anything at all, nothing in common with duplicate SACK. And so it's used by the receiver to inform the sender, hey, I just received a duplicate stream byte segment. Just wanted you to know, FYI, just saying, I'm just letting you know, no big deal, keep packets coming, but I want you to know that I got an extra segment. And Christian does a really good detailed dive into this in the SharkFest 21 Virtual Europe session number 12. So I would definitely encourage you to have a look at Christian's session to learn more about duplicate SACK. So duplicate SACK RFC 2883. It is interesting. So I would have spent more time on that, but I know I'm going to barely make 60 minutes. So I wanted you to know about that. I wanted you to know about that option. So there was a question I see a question pop up from Carl. Is DUPSACK negotiated separately? No. If you have SACK turned on and the receiver's TCP stack is able to process dupes, then you're in good shape. Or DUPSACKs, or generated DUPSACK. Okay, let's jump into our example because this is where the fun stuff really starts. Hopefully you have a good baseline now of cumulative ACK, SACK count, left edge, right edge. We're going to need these things as we go through our adventure here. So we're going to look at an actual result from a troubleshooting engagement I did a few years ago. Everything is happening in a lab environment. Customer was trying to do some testing in the lab, couldn't get their test to run, didn't make any sense. Called in for some help, and I was lucky enough to be able to go and work with them. So what we're going to see is not just high levels of out of sequence packets, but we're going to see crazy high levels of out of sequence. So we're looking at a pre-migration performance test in a lab. What they were testing was virtual automation for virtual host provisioning. So imagine you're going to spin up a new server in the cloud or even on-prem, but you want to automate virtual host provisioning So you start to spin up a base a base VM, and then you have different automation scripts that bring in patching, bring in different applications, different packages, basically building your VMs based on the nature of what it is you're building. So automation for that. So we were looking at trying to transfer these base images from a template library of VMs into starting up and provisioning and then building it on the fly. So performance was so bad in the lab that the customer had to stop their plan to migrate into this automatic provisioning model. And very, very high level, the lab configuration, there was I'm going to just quickly bring out my laser pointer. There was a management zone of the network where the image server was. That had an IPS and a firewall through some make-believe interzone routing to a different zone called the public zone, where there was a public zone firewall, a public zone IPS, and then the new VM that was going to be provisioned. And the whole goal was to download traffic from this imaging server back to where the VM was being built. And we had capture sources here in front of the image server, so close to the image server and close to the client that's being built. And then in this interzone routing, they had configured, I think they had configured some mild latency just to make it a little bit more realistic. But I believe these were all 10 gig. No, they were 1 gig links, but there should have been no bandwidth delays whatsoever. So this is our lab configuration. There were there was a firewall vendor, there were switch vendors, there was IPS vendors, there was the, excuse me, the virtualization vendors. Everybody's pointing at everybody else. They're like, hey, it's not me, it's got to be the other guy. So my job was to help the customer figure out, number one, why is throughput so darn slow in a lab environment where I've got all this bandwidth, and help us to figure out the vendor who's actually causing the problem. So what is the problem domain? Why is it so slow? So I want to just show you quickly, I took some of the Wireshark captures and I put it into a visualization tool that I use as part of my toolkit with some advanced analytics. And I want to show you what that looks like at a high level before we deep dive into the packet. So I call this a little help from our friends. So the packet capture came in, we ran it through this analytics tool, and it looks like more than half of the delay is protocol related. The other half is server delay. So we want to understand this protocol delay better. 48 mega file transfers, 117 retrans, 49 out of sequence, 20 triple duplicate acts. And we need to now make sure we level set on bytes in flight or in-flight bytes. I can't remember the Wireshark term. I think it's in-flight bytes. And we want to, it's such an important metric and it's so key to this discussion. I just want to discuss it real quick. So what does this metric tell us? The answer is it tells us the number of stream bytes that are outstanding on the network before the sender receives an ACK for the leftmost edge of the current burst. So this is something that's very important to the sender. This number is very important to the sender because it lets the sender know how much is outstanding on the network, bytes in flight. And it usually, if the number won't increase, it's usually got something to do with the sender's congestion window. So we're looking at a visual representation of bytes in flight, and we'll just kind of zoom into it. And what you can see in this graphic is, hey, we're doing slow start, we get to a point, we drop off again, we go back into slow start, we drop off again. And it's this same pattern over and over again in this lab experiment. And then we reach a point where we're not even able to get up to a high potential. So what we're really seeing is the impacts of the congestion window visually. And we're going to now jump into our example. I need to explain a little bit about what we're going to look at to give you the perspective of the out of sequence visualization with SACK analysis. So we're going to use some time-lapse photography. We're going to look at a 19 packet burst. We're going to step through it kind of like a storyboard. I went into the trace. I picked 19 packets at random, to be honest with you. There was such a mess everywhere in there. It wouldn't really have mattered where I looked. But I picked this particular 19 packet burst. And the goal is to see the nature, the count of out of sequence, but also the nature. How, to what degree is it out of sequence? And we're going to see that it's crazy, crazy high. And we're going to see how we use the SACK field to figure that out. And this is really an example, and the reason I picked it, it's a great example of how out of sequence can impact performance, and then how you can interpret the degree to which it's impacting, how bad is bad, both in terms of frequency of when it's occurring and how far the packets are away from each other. So we're going to be focusing on, well, actually, first, before we look at the payload, I just wanted to look at the ACKs together with you. So these are the ACKs coming from the client. And there's a couple of things that we want to look at together. So the ACKs correspond to one or more of the payload packets in our random sample, as you would expect. And we're going to use these ACKs to determine the arrival order for the 19 packets, just like the sender would. We're kind of pretending to be the sender and being informed by the receiver of the arrivals. So before we start, a quick pop quiz. Why are there so many ACKs? There's only 19 payload packets, but we've got all these ACKs. And the answer is, from our earlier discussion, because all of this stuff is out of order. Why does the ACK packet size change between 66 bytes, 78, 86, and 94? And that's because the SACK field is growing and shrinking with each arrival of a packet. And we'll see exactly what that looks like in a minute. This is also kind of important. Why is the receive window continuing to shrink? Notice it starts out at 44K, and then as we get farther down towards the bottom, it's at 17K. And the reason is because the receiver has to hold on to these packets. I can't hand them off to the application layer because they're not in order. And TCP has to deliver stream bytes in order to the application layer. Those are the rules. And then why do we see so many duplicate ACKs? Well, that's because it's out of order. So we're going to now dig into this. I don't know how many people have ever been to Disney World or Disneyland and may or may not remember there used to be a ride called Mr. Toad's Wild Ride. That's where we're going. I'm going to take you on Mr. Toad's Wild Ride.
Hey, so, John, sorry to cut in.
No worries.
You do have one other question in the Q&A. Okay. You might, before moving on, this might be a good spot to.
Okay, sure, yeah. Is it valid to include data bytes in an ACK with SACK if the receiver happens to have data to send back to the sender? So the other term for that is piggyback ACKs, where you're sending payload back with an ACK. I think, Carl, that's what you're asking. Is it valid to include data bytes? So it's an interesting question because the notion of piggyback ACKs are the app layer on the receiver is I'll use the word stimulated to send data back to his partner. And if I can't offload payload up to the receiver's app layer, I may not be able to trigger that stimulation, for lack of a better term. So if it's a synchronous behavior, if it is a synchronous behavior, then I doubt you would see data packets going back. But if the nature of the application was totally asynchronous, where either side could be sending to either side at any time for any reason, then you could definitely see payload in the ACK packets for sure. I don't think there's any reason why you wouldn't, because it's independent behavior. So hope that helps with that question. this will be 19 slides, but it's a storyboard. So we're going to go through them rather quickly. The top portion of the slide is going to show you which packet was just received. The bottom portion is going to show you the decodes. And each slide represents a new packet being received and the state, and this is kind of important, the state of all previously received packets. So let's do some quick orientation. Notice we have our first column is public, says public frame, that's nearest to the client. Sorry, the receiver, who's the client. And then the second column is the management frame number from. So these are two different captures that basically I brought together sort of side by side for analysis. So the management frame column is the frame order as seen in the management capture. And notice they all leave in order. 2, 3, 4, 5, 6, 7, 8, 9. They're leave this. This is the sender, so they're all leaving in order. So that's good to know. When I put a red box around a row, that indicates in our storyboard that a packet was just received, bracketed in red, and green indicates previous frames that were received will be bracketed in green. In the bottom, we'll have the TCP header from the ACK, as well as the SACK field from the TCP options header. So we've got some arrival context, we've got some state information, we've got some decodes that's going to help to tell the story. So if you're ready to start our wild ride, fasten your seatbelt, focus on the cumulative ACK and the SACK values, double check your understanding. Ask if what you're seeing tracks with our earlier study of ACK and SACK. And let's, to start our journey, let's acknowledge that, or let's state that the receiver says, hey, I'm ready for this big ugly sequence number that ends in 6095. So that's how we start our storyboard. So there's one more graphic here that I just added over the weekend. This black line is going to show us where the cumulative ACK is pointing. So if you notice, we declared 6095 was the next thing that we wanted to see. So our cumulative ACK pointer is pointing to, hey, I'm ready for this packet 4692. So first packet received is showing in red, and it's out of order. So because it's out of order, we have some SACK fields. Notice we have a left edge, we have a right edge, we have our cumulative ACK that says, hey, hey man, I was waiting for 6095, but I didn't get that. I got instead 8991 to 0439. So that's our first packet being received. Here's our second packet now. So I turn this block green because it's in the buffer. I just received this packet. My cumulative ACK has not changed. It's still saying, hey, I'm waiting for 6095. And you can see that in the header down here. I'm waiting for 6095. And I now have two SACK blocks. One that goes from 8991 to 0439, and one that goes from 769, which is what I just received, this one, and 8912 going through left edge 7679, right edge 9127, representing this packet that was just received. So that was the second packet. Here comes the third packet. So the third packet came in, and it's actually the one I was waiting for. So now we can update the cumulative ACK saying, all right, we're ready now for 7543. And oh, by the way, we still have these exact same two SACK blocks that we had a minute ago. I've received them, they're out of order. I'm holding on to them as long as I can. Keep sending me data. Hopefully it'll all work out. Here comes the fourth packet. And if you notice, it's jumping now down here. So we just added to this segment area here, and the right edge just changed in one of the SACK blocks. So it changed from 9127 to 0575. So now we have a continuous area here. we have this area here and we have this area up here. We've got stream bytes in order up to a certain point, and we've got 2 more out of order blocks. So now packet 5 arrives, it's in red here, and now we're adding to this part of the stream bytes. And now we've changed the right edge yet again. We're still waiting for 77543. That's why this black line is still pointing here. But we've now received something that helps fill out some of our gaps, but we're still not in order. I can't give any of these off to the application layer. Notice also when we got the 5th packet that the left edge, right edge order, it flipped. So I'm going to go back one. I'm going to go to here's the 4th packet. When we see the 5th packet, notice that the order flips, which just illustrates the arbitrary nature of the order within the headers TCP options field. So they can change. It doesn't mean anything's broken. It's allowed. So if you read the RFC, it would probably say something about you can keep them in order if you want to, but you don't have to. And if I'm a sender and I'm getting these SACK blocks, I don't have to I don't have to expect strict ordering. And I'm almost out of time, but I'm almost done. 6th packet comes in. Notice that the 6th packet filled in this gap right here. So we move our cumulative ACK down and we get rid of one of our SACK blocks. This is the only remaining block open. 7, part of this wild ride. So here comes packet 7, and now we're 6 packets ahead of where we're more than that. We're like 10 packets ahead of where we're supposed to be. And we've created a new SACK block. Packet 8 comes in. Now things get even more exciting. Notice now we're kind of in this middle area here. And now we have 3 blocks that are being declared by the receiver. Cumulative ACK has not changed. New packet comes in. Now we have 3 SACK blocks. Packet 9, we now have, fortunately, something that arrived expected, but we still have these 3 SACK blocks that have been received. Cumulative ACK comes down now to 3335, which is what we'd like to see next. Packet 10 comes in. We jump way down here again. You can see it in red here. Packet 11 comes in, fills in some space here. All of this stuff is still out of order. Everything you see in red and green is out of order. Packets 12 and 13 come in down here. To save a slide, I put them together because they arrived in order, but they're not where they should. It's not the stream bytes we were expecting. So we still have 3 blocks out of order. And then packet 14 comes in, and we filled in the space between this green block and this larger green block. So they're still out of order, but it's now one contiguous block of out of order packets. So we go from 3 blocks down to 2 blocks, and we're almost done. Here comes packet 15, fills in the row. We now have only 1 contiguous block that's out of order. Here comes, and I think Carl had a question earlier about can the left edge ever update? And here's an example of that here. When 16 came in, it was at the a lower left edge number than this existing green block. So the left edge was updated here. Packet 17, packet 18 at the end. So the right edge gets updated. And finally, packet 19 comes in and everything is finally here. And the ACK points to the fact that we're ready for the next wild ride. So it's been a long, strange journey. All the data has finally arrived. And when I was troubleshooting this with the customer, and I realized we're out of time, I'm going to maybe go 3 minutes and then we'll stop for more questions. Because I think there's 15 minutes for questions. Is that right, Chris? Does that sound possible?
Yes.
Right? Okay.
Yeah, exactly. You have up to 4:45 Pacific time.
Okay, perfect. Okay, so we're almost done. So, yep, it's been a long, strange journey. The data has finally arrived. We did get to the bottom of this with the vendor. The guilty vendor said, yeah, I see what you mean. It is me. And they went back and did a code update. It got a little bit better, still not good enough. But, we were, by using the packet analysis and really focusing in on this crazy out of sequence behavior, we were able to help the customer understand, number one, why is it so slow in the lab? So we explained that, congestion window closing, and who's the vendor. So buffer management issues happening someplace in that path. Is it first in, first out, last in, first out? Is it a UFO? Is it iffy? Who knows? It was definitely a buffer management issue, though. Packets were not leaving in the order they came in. So no question about that. And I think we're going to stop here. When the deck gets posted, you'll see there's an appendix section with a few additional points to be made about crazy firewalls and some other details. TCP SACK related. So that'll be uploaded to the retrospective page. So we'll pause here for questions and comments before we wrap up.
Okay, you have a couple, John. In the chat, there was one from Blaze.
Okay, in the chat. Okay, so
if we can only have 3 SACK blocks.
Okay. Well, so what happens is we don't have any way of informing the sender that this segment just got received. Now, it's a really interesting question because I don't know, does that mean, will the receiver hold on to it in the hopes that he could report it later? Or does he just have to abandon it? And honestly, I don't know the answer to that. And it probably could be left up to the implementer as well. If the people who wrote the stack or a new version of a stack said, you know what, we can figure out a way to keep these in memory, maybe, and then report them opportunistically, or maybe we just have to abandon it and the sender's going to have to retransmit it. So the answer is I don't know, but that's my speculation. So let's see, does the occurrence number in Wireshark change? So we saw that we could flip-flop in our example. We saw that they don't have to be in a strict order or in a persistent order. So they could go either way. And Chris, do you want to jump in on that as well?
Sorry, John, I didn't get the context on that one.
Well, I'm looking at the Q&A screen. It says Chris would like to answer this live. So
no, sorry. I was just tagging it as being answered live. Sorry, that that would be confusing.
It's cool. Sorry. So Sheila's question, does the occurrence number change? And the answer is, I believe it will. So you'll see it move around in the columns. The columns won't change. Whatever's in occurrence 1 will be displayed in that column, but you might see what's displayed there move between columns. Hope that helps. Patrick had a question also on DupeSACK. Does it have the same ACK left edge, right edge? If not, how do you tie it back to initial DupeSACK? So Patrick, that's a really good question. Also, DupeSACK is almost like a different mechanism. And if you take a look at Christian's session, he's got a great example where I'm only reporting duplicate. So that's first case. And then another example where he's showing how the receiver is reporting both missing blocks and duplicate segments being received. And I didn't have time to fit it into this session. That's why I wanted to refer you to Christian's, because I thought it was really well done and it does cover that exact topic. Frank, I have a trace with a bunch of DSACs that are all on keep alives. Anything you can tell me about what this means? Any idea who gets the indictment? Guilty. Guilty is charged. Yeah, so keep alives, it's interesting. Depends on the version of Wireshark, and in my case, some of the advanced analytic tools that are kind of a wrapper around Wireshark. Keep alives will show up sometimes on my tool as retransmissions when they're really not retransmissions. I mean, technically, yes, it is a retransmission. Then usually keep alives are a 1 byte, the last byte that was sent, and it's just a way of doing a keep alive. There's also 0 payload keep alives, but that's why it's showing up as a duplicate SACK saying, hey, I've already received this 1 byte like a whole bunch of times. Sometimes what I've done, and I'm not sure if I did this in Wireshark or in a different tool, is if the payload was a single byte and I convince myself that it's a keep alive, I really don't even want it in my capture. And I think I edited it out just because it's good to know that it's there. Oh yeah, the sender and receiver are using keep alives. Okay, good to know that. Great information. Now let me get it out of my way. So maybe I make a copy of the capture file and get rid of packets that have a payload length of 1. It's risky because you might get rid of something that's not duplicate SACK, but that's how you could use. There is a dup SACK flag in later releases, I believe, of Wireshark as well, and you could use that as a filtering mechanism to say get rid of these 1 byte keep alive, packet length is 1 or payload length is 1 and it's a dup SACK. I don't want to see it. Get it off the screen. So you could just say, if it's not that condition, I don't want to see it. Dup SACK, does it have the same left edge, right edge? If not, how do you tie it back? I don't know that. I'm not sure if Christian Session had multiple duplicate segments. I can't remember. He might have an example of that. Does it have the same ACK left edge, right? So the dup ACK, yeah, you'd really have to look at his examples because there's some cases where you're seeing a segment twice or on the second time, but it's still behind the cumulative ACK. I don't know if I can describe it in words. I'm too dependent on visuals. So if you want, feel free to reach out to me on email or Twitter or whatever, and we can talk about that some more. That's an interesting question. Oh my goodness. So is any other questions? Oh yeah. So Neil has a great question. One thing I've seen some devices rewrite sequence numbers. Yeah, that's exactly. Yeah, there's an example in the appendix of that coming from I don't think we are supposed to use vendor names here. Coming from a vendor firewall, where and this might have been in an older version because it was quite a few years ago when I saw it, but the SACK fields were different ranges, different magnitudes away from the cumulative ACK. And I'm trying to remember now if you had relative ACKs turned on, if you would notice a difference. If you did not have relative ACK showing, the display option for TCP show relative ACK, if you had the absolute ACK, you totally would see it. I'm pretty sure you would also see it, evidence of it with relative ACK as well. But my discussion with firewall admins is, why do you need that on? If you're inside the data center, why do you need to rewrite sequence numbers? If you're trying to do high level or even low level packet analysis, it creates problems for you for your troubleshooting. So I can definitely see it on the perimeter of a site. Yeah, that's fine. But when you're inside the site and you're past the DMZ and you're in the protected area of the data center, it's worth a discussion to say, do you really need that feature turned on? And if the answer is yes, the answer is yes. but it's worth the discussion. So let's see. I think that's everything. So I think it's a wrap. We're leaving 4 minutes